after this. So a factorial of a positive integer is the product of the positive integers less than or equal to that number. Okay, so for example, if you have n factorial, right? Factorial, the symbol for factorial is the exclamation point. So if you have this isn't like, you know, n, right? Like we're not excited about the letter n. This is n factorial, which means the way to evaluate it is n times n minus 1 times n minus 2 times n minus 3, all the way down to 3 times 2 times 1. A real example would be if you have 8 factorial, right? Whatever the number is, 8, you start with that number and then you multiply all of the integers from that down to 1. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So if it's 1,000 factorial, it's 1,000 times 999 times 998 times 997, all the way down to 3 times 2 times 1. Okay? So, one thing you need to know, 0 factorial is 1. That you need to know. 0 factorial is 1. Memorize it now. 0 factorial is 1. I can tell you a little bit of why later once we start using it, but it is what it is. Just like, what's 3 to the power of 0?
3. No, 1.
1. We know this, right? 0 factorial is 1. Okay? Okay, now, let's talk about, why is it doing that? Okay, so let's talk about permutations. Okay, when the objects in a sample space are arranged so that order is important, each arrangement is a permutation. Okay? And factorials are used in finding permutations. So for example, if I gave you 3 letters, A, B, C, there are many ways of arranging those letters, right? One is A, B, C. One is A, C, B. One is whatever, right? There are many, many different ways to arrange the letters, right? But now if I give you a condition, I said arrange the 3 letters so that they form a word. Now, C-A-B, do you see how it's not just randomly arranging the letters, but it's arranging the letters such that the order matters, the order of the letters matters? That's a permutation. You see that? If I just told you, give me all the ways you can arrange ABC, you could do ABC, ACB, BCA, right? BAC. The order doesn't matter. But if I told you, arrange them so that you form a word, now the order matters. Okay? So that's a permutation. Okay. All right. So we got a couple people here. We got Erica, Jasmine, Tara, Becky. They're on a softball team. The coach wants to consider all the possible ways the 4 players could bat first, second, third, and fourth. Find the total number of permutations. Okay? So, because there are 4 people, okay, and you want to arrange them with a certain order, right? This is a permutation. So the total number of permutations is 4 factorial. So that is 4 times 3 times 2 times 1. Is this similar to what we were doing yesterday? How many different ways are there to arrange these 4? So in the first slot, you have 4 options. Then once you choose 1, in the third slot, you have 3 options, then 2 options, then 1 option. So together, that makes 24. And that's totally something that you can do without a calculator, right? Yes. Okay, so a lot of these you can do without a calculator. Ray and 5 of his friends go to see a movie. In how many different ways can they sit together in a row of empty seats? Well, that's 6 factorial, which is equal to, okay, go ahead and take out your calculators, and I'll show you how to do it on your calculator, and wants to select just 3 students, not all of them, just 3 students to go up to the board one at a time. So 3 need to be selected. How many different ways can this occur? So if there are 30 students, how many choices are there for the first student to go up? 30. Then for the next student, how many choices are there? 29. 28. And then 28. So this is where you stop. Okay? 29, 28. And then that will be 24,360. Okay.
Oh, okay.
Because we only have 3 slots. Okay, so now, does this mean like I have to write it out every single time? What if I had like 1,000 students, right, in a school, and I had to pick like 57, right? I'm not gonna sit there and do like 1,000 times 999 times 9, like 57 times, correct? There has to be another formula. Like this is easy. You're only choosing 3. But what if I had to choose 57? I can't just keep like multiplying numbers like this. That's just silly, correct? So there is a formula to do what we just did a little bit more directly. The formula is the permutation formula. And it says the number of permutations of n objects taken r at a time, okay? So for example, 30 students taken 3 at a time is this. N factorial over n minus r factorial. So in this case right here, we had 30 students. N is 30. We're taking 3 of them. R is equal to 3. So let's see how the formula plays out when we do that. It's permutation, n permutation taken r at a time. So that's going to be n factorial, 30 factorial, over 30 minus 3 factorial. Okay? How much is that? 30 factorial over 27 factorial. And now you're like, okay, great, but that's so not what we did. Well, is it though? Let's see. What's 30? It's the same. 30 times 29 times 28 times, it's 27 times 26. So that's 27 factorial is all the rest of it. Over 27 factorial, that goes away. And look, you've got the same thing left. Okay? So this formula is another way that we could have evaluated that, because it still ends up with 30, 29, 28.
Or you can just put it in your calculator. Well, you put it.
You got to know the formula. Because like I said, Yali, if right here, we're only choosing 3 students.
No, like after you do the formula, like
Right.
the 30.
Right. Yeah, after that, you're going to put it in the formula. But and I'm saying is, after that, you're going to put it in your calculator. But what I'm saying is you need the formula, because if you're not choosing 3 people, if you're choosing 74 people, then you got to do the formula. You can't just do this.
Right.
Okay. Yeah.
I don't understand how you use 30 times 29 times 28.
We're going to do it again. We're going to do a whole lot more right here. Okay? We're going to do a whole lot more right here. Okay. So let's do these. Okay. So 10 factorial over 8 factorial. Let's write these out. This is 10 times 9 times what? 8, 7, 6, 5, 4, 3, 2, 1. I could sum that up as 8 factorial. Okay? Divided by 8 factorial. Well, 8 factorial and 8 factorial goes away, and this is just 90. Okay? So basically, when I'm writing out the numerator, I always pay attention to what I have in the denominator. And when I get to a point where I have this number, I stop and I do factorial so I can cancel it out. So 16 factorial is 16, 15, 14, 13, 12. Now it's going to go down from 12. Starting at this point, it's 12 factorial. I stop there because that's the number I have in the bottom. So 12 factorial, 6 factorial. Okay? But hang on, what's 6 factorial? 6, 5, 4, 3, 2, 1. Okay? So look at what I do. 12 factorial goes with 12 factorial. But now I can cancel some more things out here. Okay, you just have to be like smart about it. So look, or wise about it. 5 and 3 on the bottom are the same as the 15 on top. Correct? So that goes away. Lots of things you can cancel. You have to be like clever. This 2 cancels with the 14 and I get a 7 there. Right? I mean, you could do it more than one way, for sure. What else can we do? We can cancel out the 6 and the 16. I can divide by 2, so I get 3 and 8. Right.
But you can do the 4 would be more better.
It's up to you. It's really preference. So what do I have left? 8 times 7 times 13.
You can divide the 8 by 4.
Oh, yeah. Okay. Over, let's do it. 3 times 4, right? And I can divide this one. 2 and 1. 14 times 13 is 182 over 3. Okay? And I know some of you are asking me, well, why can't I just plug it into the calculator? Because Algebra 2 honors. Because we want you to be able to process numbers without having to reach for your calculator all the time. We want you to have some sort of number sense. Okay? So, all right, let's do another one. 7 taken 2 at a time. So 7 factorial over what? 7 minus 2, which is 5 factorial. So this is 7 times 6 times 5 factorial over 5 factorial, 42. Okay, what about this one? Remember, the higher number always goes on top. 6 factorial over how many factorial? 2 factorial. So 6, 5, 4, 3, 2 factorial.
Wait, why isn't it 4 factorial?
Because it's 6 minus 4. The formula is n minus r. 6 minus 4. Okay, so look. So look at what I have here. 20 times 3 is 60, times 6 is 360. Okay? Okay. Now, the librarian is placing 6 of 10 magazines in a school showcase. How many ways can she arrange the magazines in the case? Okay? Okay, so this one, you have 10, you're choosing 6. So it's P, 10, 6. 10 factorial over 4 factorial.
Does it matter what was before the P?
Yes, the n, the big number, n. Okay? And that goes first here, that goes first there. So this is 10. You know what? Let's plug this into the calculator. Can somebody plug it in for me? 151,000.
151,200.
Okay, thank you. Okay, thank you. She was, yeah, thank you. Let's give people, let's give each other opportunities. So, okay, so again, let's think about this. Let's think about this situation of you're picking 6 magazines and arranging them on a shelf. Think about how that order matters versus if you were to pick 6 number 2 pencils out of a box and arrange them. Would the order matter there? No, right? But here, they're different magazines, right? So you have like you have a science magazine and a math magazine, right? Like the order matters, okay? All right, because what other magazines are there if not for science or math, right? Okay, what about permutations with repetition? What if out of the 6 magazines you did have 2 that were the same? Those 2 can be flipped and nobody would know about it, right? So those are ones that, you can have repetitions. So the number of distinguishable permutations of n objects in which one object is repeated R1 times, another object R2 times, and so on is this. So this is the one with repetition. Okay, so look at this one. On a game show, you're given the following letters and asked to unscramble them to name a U.S. river. What river do you think? That's the Mississippi River. If you selected a permutation of these at random, what is the probability that would spell the correct answer of Mississippi? So if you put all these tiles in a bag, and you check out 1, 2, 3, 4, what are the chances that it'll spell out Mississippi? Now, if you had this S first or that S first, would it make a difference?
No.
The I's? No. So the repetitions will not make a difference if you switch them. So, yeah.
When I looked ahead in the packet, I saw this, and you know how we had like Sokotoa and
You thought it was that?
I was like, trying to read it. I didn't read the
Okay,
problem.
so how many total letters are there? 11 total. So that's N. Okay? So what's the formula? It's N factorial, okay, over R1 factorial, R2 factorial, and so on. Okay, so how do the I's, how many I's are there? 4. How many S's? 4. And how many P's? 2. Okay? So here, you put the number of times each one repeats. So 4 factorial, 4 factorial, 2 factorial. Okay? That gives you 34,650. Right. So now let's go back to the question. It's not saying how many different ways are there. It's saying what is the probability that they would spell the correct answer. So the probability that you get Mississippi is 1 in 34,650. Okay? Now, this is a permutation. All this was permutations. Now, let's go to the combinations where order is not important. So, for example, if I had, okay, you guys want to know how many pens I have in here? Because you never know when you might need another pen. You never know when you're doing a permutations lesson. So if I had to arrange these, order matters, right? Because the red and the blue are different, yeah? But if I took these out, and if I had to just arrange these, would order matter? No. This is a combination. This would have been a permutation, okay? So, the setting here, it used to not like respond to touch, but now it is. Okay, so a combination is a selection of objects in which order is not important. So let's identify each of these as a permutation or a combination, choosing 3 different pizza toppings from a list of 12. Doesn't matter if you choose mushroom, pepperoni, then olive, or olive. No, the pizza will look the same regardless, so that's a combination. the way the pizza looks at the end of the day, will it matter if you chose them in a different order? It doesn't matter, but you're only choosing 3. Elijah, you're missing the point. The point is, you have to choose 3 toppings. Does the order in which you choose the 3 toppings matter? No. So it's a combination. Okay? Okay. Choosing team captains for a football team. You're going to be a captain and you're going to be a captain. Does it matter if I give your name first or your name first? Does it matter?
Yes.
Does it? No, because you're both going to be captains. So it doesn't matter.
Oh, okay.
Yeah.
That was like random.
So it's a combination. Choosing first, second, and third place in an art competition. So that's a permutation, right? Because if I told you these are the 3 names for first, second, and third, you can't mess up the order, right? Okay. So the combination formula is different. Do you have to memorize these? Of course you do. That's what flashcards are for. Okay? This is n choose r, n c r. It's n factorial. So look, you have 2 numbers again. It's the first one factorial, the difference, then the second number factorial. First difference, second. First difference, second. That's how I remember it. So let's evaluate. First difference, second. Even at my age now, this is how I remember that formula. When I teach this in pre-calc honors, for one thing that we use it for, that's how I teach it to them as well. So, what do we got here? 8, 7, 6 factorial, because it shows up on the bottom. 6 factorial, 2 times 1. So, 6 factorials go away. Yep, so 28. Yay! Loving this. It's fun, right? So 10 factorial over what? 5 factorial, 5 factorial.
Oh my god.
5 factorial over 5 factorial. 5, 4, 3, 2, 1. Okay. 5 factorials go away. Okay, look here. 2 and 5 cancel with the 10. Okay? This 1, 3, and this 9, that makes it a 3. This 1, 4, and this 8, that makes it a 2. You just have to be, like, neat and organized. Because if you've got numbers all over the place, then it doesn't work. So what do we have here?
Wait, why did 200?
Good. Okay. Yes, Lexi and our manager wants to create a display for 3 mannequins. How many ways can she choose from 20 different shirts? So she has to choose 3 shirts to put on mannequins. And again, the order doesn't matter, right? She could have like, like they could have like the purple and the blue and whatever. So,
20 C3?
right, C23. Okay. There is a button on your calculator that does this, by the way. Let's go to your calculators. Go to menu. Go to probability. This is why I want to teach you where the... Go to combinations. Okay. Here, it's 20, comma, all sorts of syntax here. Comma is right below the pi next to the O. 3, 1140.
Okay. That's the answer?
Yep. Now,
And that can you do it myself, right?
when I tell you to show work, you better show the work. Okay? Or you can do it that way, huh?
How would you put like 17 20 minus 3 is 7?
Yeah. Well, it's like 20 times 19 times 18 times 17 factorial. Then it goes away. They're fun. These ones go away. The combinations go away more quickly than the permutations. Okay. If 3 points are randomly chosen from those named on the rectangle shown. So here you have letters A through H. You're going to choose 3 of them. what is the probability that they lie on the same line segment? So what is the probability? So here's what it's asking. How can you get ones on the same line segment? So if you choose 3 and you get CDE, or if you choose 3 and you get ABC, or if you choose the 3 and you get the EFG. Now, does it matter if you got E, then F, then G, or G, then F, then E? No. So this is a combination. How many different ways are there to get these 3 letters? Okay, that's a combination. So this is C, 8, 3. Let's do this by hand because it's easier. 8 factorial, 5 factorial, 3 factorial. 8, 7, 6, 5 factorial. 3 times 2. Okay? So look, lots of things cancel here. 5 factorial. The 6 and the 6. And then it's 56. Like,
when I did it, I did 3 and 6 and 8.
yeah, see? It's endless fun. That's a permutation. Or maybe it's a combination, actually, because the order doesn't matter. See? Huh? That's like a nested combination. A teacher wants to form a committee of 5 students. There is a 32-person class. Okay, how many ways can we choose from the committee? Again, does the order matter? Combination.
32. Are we doing it by yourself?
Do it by yourself. Plug it in the calculator. Don't tell me your answers.
We can do calculator.
Yeah, this is a big number. So that one, okay, so a password, back to the passwords. 4 different letters from the alphabet. What is the probability that someone guesses the password on the first try? So, okay. Is this a permutation or a combination?
Permutation.
It's why? The order matters. So, if I have L, Q, R, S, if that's the password, okay, so it's not just any 4 letters. It's 4 letters in a specific order. Because if I choose 4 letters and I get these letters, but I somehow order them like this, right? That's wrong. So the order does matter. It's not. Yeah, it says, yeah, it doesn't say that they can't. So if I do pick the correct 4 out of a hat, the way in which I arrange them also matters. Okay? SQRL, that's a thing. What is SQRL?
Squirrel.
No, that's an actual thing. Okay, I think it's a way to take notes. Oh my God, it's like a thing from the past. Okay, I need to look into this. So this is a permutation. I have 26 objects taken 4 at a time. When you put that in your calculator, you get 358,800. What is the probability that you guess that on the first try? It's this many. I was mixing that and the piece.
I want to see like how many zeros there's in the percent.
So 358,000.
Yeah.
Wait, I thought 358,800.
Oh, it's 800. Sorry. It's 800. Okay. Quick explanation of how to do these. This is one time, because we're short on time and because we're all at different levels, I want everybody to just focus, period. So this is one time where I'm going to ask for no participation, just listening, okay? Okay, all right. So I have to factor this. You first count how many terms this has. 1, 2, 3. This is a trinomial. Next, ask yourself, are the first and the last perfect squares? X squared is a perfect square. 12 is not. So now, I have to write down 2 sets of parentheses. In the first slot, I need 2 numbers that multiply to the first one, x squared, x and x. Now I need two numbers that multiply to positive 12, add to positive 8. So 6 and 2, and that's it. Okay. Now, next one, very similar. Trinomial. Oh my God, what's happening here? Trinomial. Okay, now I ask myself, is the first a perfect square? Yes. Is the last number a perfect square? Yes. When it's a trinomial and both are perfect squares, then this is a special pattern of factoring, and it's one parenthesis squared. Okay? How do you do this? You take the first one, you take a square root. You take the last one, you take a square root. Whatever that sign is, you put that sign here. Now, you have to try one more thing. Does 2 times negative 4 times x equal that middle number, negative 8x? Yes, that's how we know we did it correctly. Okay? All right, let's do one more. You come over here, and this is all sorts of things here, but then you realize, oh, wait a minute, this is a binomial. I have z's everywhere. I can factor out a z. What else can I factor out? Between the 36 and the 9, what GCF? 9. Okay, so now I get 4z squared minus 1. Okay, now this is a whole other issue. Can this be factored further? Well, let's see. For the first time now, I don't have a trinomial. I have a binomial. So ask yourself, are these perfect squares? Yes. Do I have a minus in the middle? Yes, that's key. That's key. So I get 9z. Now you open up two parentheses. Take the square root of the first one, 2z, 2z. Take the square root of the last one, 1, 1. And now, one gets a plus, one gets a minus. It doesn't matter which one. Okay? All right.